Thought I had it set up to record automatically. Okay, so that's what we just did is vector addition visually, but we also need to do vector addition mechanically. So if someone provides us with a vector, can we add them together? And addition of vectors is very simple. If somebody gives you a vector u, which has two components u1 and u2, and then another vector v, which has components v1 and v2, all we do to add the vectors together is add their components. So we add u1 and v1 together, whatever numbers those are, and then u2 and v2 add those together, and that's the sum. So it's very, very simple when you add two vectors together. And then if you subtract two vectors, it's the same thing except you subtract the components. Now, let me ask you, is addition of vectors commutative? In other words, is u plus v always going to be the same as v plus u? What do you think?
Yes.
Does vector addition commute? I heard yes. Now why? Why would that be true?
Because for vectors, position doesn't really matter. It's just the magnitude and the direction.
Okay.
And when you showed us how to add them on the visual, it had the same direction and magnitude.
That's right. So it doesn't matter. It doesn't matter. Visually, we saw that it didn't matter which one we put first. But mechanically, I want you to look at something. When I say u1 plus v1 and u2 plus v2, we're adding two numbers together, right? Now, in addition, in regular old addition, does it matter which way we add? Like 3 plus 2 is the same as 2 plus 3, right? So because addition of numbers is commutative, you can switch the order, so is vector addition. Doesn't matter which order you do it. Now, how about subtraction? Does the order matter in subtraction? Is u minus v going to be the same, this is the question, as v minus u? Are those the same? What do you think? Look at this operation, u1 minus v1, u2 minus v2. If I switch those, are you going to get the same answers?
No.
No, you will not. Not in general. So vector addition is commutative. You can flip the order. Vector subtraction is not. The order matters. Okay, the order matters with vector subtraction. Now, the next little part of this note is the exact same thing as up here, except it's telling you what would be going on if you had vectors in three-dimensional space. So if you have a vector that has three components, v1, v2, v3, and another vector u that has components u1, u2, u3, then vector addition means you just add up the components. Vector subtraction means you just subtract the components. Order would matter in subtraction, order would not matter in addition. All right, any questions? I think we have an opportunity now to do an example. Not yet, I think, hold on, it's coming. Got to get some other stuff out of the way. Okay, so here's what we know now. If somebody gives us two vectors, we can add them and subtract them, right? Next thing to talk about is multiplication. Now, this is very important that you understand. There's a distinction that I'm about to make that I want to make sure you understand. When we're talking about numbers, okay? Think about, when you learn numbers as a kid, you were taught 4 operations, weren't you? Addition, subtraction. I'm going to do the old school multiplication and division. Those were those 4 basic arithmetic operations, right? So you were taught as a kid that, hey, look, if you have two numbers, we can add them together and we get a number, right? If we have 2 numbers, we can subtract them and we get a number. If we have 2 numbers, we multiply them, you're going to get a number. If you get 2 numbers and divide them, you're going to get a number, right? So this is what we've done in the past is very natural. Start with 2 things, do one of these operations, you get a number, right? Now with vector addition, what we just talked about, if I take 2 vectors and add them, what do I get out?
A vector.
A new vector, right? A new vector. Okay, and if I take 2 vectors and I subtract them, what do I get out?
A vector.
A new vector, right? Okay, so now let's talk about multiplication. If I take a vector and multiply it, there's a distinction here. I have to ask myself this question. There's 2 cases we can have here. am I multiplying a number times a vector? Or am I doing multiplication where I have a vector times a vector? Right? Understand the difference here. Because a vector is not a number, right? So when I say multiplication, you have to understand, are you talking about taking a number and multiplying it by a vector, or are you talking about taking two vectors and multiplying them together? Those are two completely different things. We didn't have that with numbers, right? Numbers were just numbers. So there's a major distinction that we have to understand here. We are going to talk about right now this case where you have a vector and you're going to multiply it times a number. And that is called scalar multiplication, okay? Scalar multiplication of a vector. So scalar multiplication means we're going to take a vector. We're going to be given a vector, v, and we're going to be given a number, a scalar, c. So c is just some real number. And what we want to do is multiply them together. Take the number and multiply it times the vector. Well, what happens when you do that is that it's going to change the length of the vector. It's either going to stretch it out and make it longer, or it's going to shrink it, or perhaps even flip it into the opposite direction. It depends on the number you're going to multiply by. So I'm going to show you just visually down here what's going on, and then we'll actually draw a final conclusion. Oops, I can't make this any bigger. Okay, so we have a vector. And right now I'm multiplying that vector v, which is this black one. I don't know if you can see that. I'm multiplying it by 2.5. So what happened? What happened when I multiplied that vector v by 2.5?
It got longer.
It got longer, right? Stretched it out. Did the direction change? No, direction didn't change. So multiply by 2.5, it got longer. Okay, let me pull it back here. What if we multiply it times 1? Well, it would just be the same vector. Okay, so it doesn't stretch it out at all. What if I multiply by 0.5? So what happened there? Can you tell? It's hard to see this.
It cut it in half.
It cut it in half, so it's half as long, but it's still pointed in the same direction, isn't it? What if that number is negative? Ah, look, if I multiply it times -1, what happens? Flips direction. It's the same length, but now the direction is in the opposite direction, right? And if I keep on getting bigger negative numbers like -2, it's now twice as long, but in the opposite direction. Okay, so scalar multiplication, all it does is stretches your vector out. You maintain the direction. Unless it's negative, then it flips it to the opposite direction. And that's what this is saying here. Let me clear this all out here. It says, if you take c times v, then if the absolute value of c is bigger than 1, it's going to stretch it. If the absolute value of c is between 0 and 1, like a fraction, like 1/2, it's going to shrink it. And if c is negative, it flips the vector completely over. Now, the good news is that when we do the actual multiplication, it's easy to do. So I'm going to give you a specific example. Let's say I give you the vector v is, let's say 2, -3, okay? So if I wanted to know what -2v was, this is scalar multiplication. I'm taking a number and I'm multiplying it times v. And that all that means is I'm taking -2 and multiplying it times this vector. And it behaves just the way you would hope it would behave. And this is what this little property is saying here. All you're doing is really kind of passing the 2 into each of the components, just multiplying each of the components by, sorry, -2. So you're going to get a new vector, -4, and then +6. Okay, so scalar multiplication, very straightforward in terms of the mechanics. You just kind of distribute the number through. Okay, so this vector is -2v is this vector. It should be twice as long as this vector, but it should point in the opposite direction. Okay, scalar multiplication is nice, right?
Yeah, it's very plain.
Yep. Okay, so now parallel vectors. Any two non-zero vectors are said to be parallel. Any two non-zero vectors are said to be parallel if they are scalar multiples of one another. Okay, this is a different definition from what you've learned about parallel in the past. In the past, when you've talked about parallel, you've talked about parallel lines. And what is the condition for two lines to be parallel? Do you remember what the condition is for two lines to be parallel?
They have the same direction.
Okay, for lines back in like college algebra, if I had two lines that are parallel, they'd have to have the same
Slope.
They'd have to have the same slope, right? If they have the same slope, then they're parallel lines. But we're not talking about lines. We're talking about vectors. So if I have two vectors, for them to be parallel, all that has to happen is they have to be scalar multiples of one another. So let me give you an example. Let's say I take this vector right here. That's supposed to be straight. And then what if I say I take this vector here? Are these parallel? I see Donald shaking his head yes. Why?
Is it because the big one could be multiplied by like a -5 or something?
Yeah, so if we look at this big vector, right? If we multiplied it by a negative number, it would flip it over, right? So it'd be pointing out like in this direction now, right? If we multiply by a negative number. And then let's say we could take a number like, I don't know, maybe like 0.25, that would shrink it, right? So if I shrink it, it would be like this. And that's the same as this one. So even though they don't point in the same direction, they're scalar multiples of one another. So like if I call this, let's say u, this looks like it could be like -0.25 u. You see, I flipped it over and shrunk it, but they're still called parallel because all I did was multiplied u by a scalar in order to do it. This is a very, very big distinction that you have to understand in our language with vectors. You can have vectors that point in the opposite directions and they're still considered parallel. All right. All right, now we have another definition, the magnitude of a vector, the magnitude or length of a vector. So just like you would imagine when you're talking about the length of a vector, you're saying if you measure it, how long is it, right? So it's very easy to find the length of both either a two-dimensional or three-dimensional vector by using this formula. And this is the notation we use. It's like the absolute value around the vector. And so all you do is take the square root of the sum of the squares of the components. So if you have a two-dimensional vector, you're just going to take the square of each component and then add them together and square root it. That will give you the length of the vector. And that just comes from the idea of if you have a vector and you construct a right triangle, we know that this distance here is V1, that's the X component. And we know this is V2, that's the Y component. And so if you want to know this side, the magnitude of the vector, then all you have to do is Pythagorean, right? V1 squared plus V2 squared should equal that squared. And then you have to take the square root. And that's where this comes from. And it works the same way in three-dimensional space. So anytime from now on that you hear me say, hey, we need to find the magnitude or find the length of a vector, we've got to run that computation. All right, finally, we have some problems to work on here. So let me grab this problem. Put it over here. All right, so what we want to do here is find and sketch the following. So what I'm going to do here is I'm going to start out by drawing these vectors. So I'm going to put a grid here for myself. These are two-dimensional vectors, so this should be pretty okay in terms of graphing these. So let me put the vector 2, 3. The vector 2, 3 would be to the right 2, up 3. That's the vector V. Now remember, I can move V around anywhere I want, right? That's where I'm going to put it initially. The next vector is the vector U is -1, -4. So to the left 1, down 4. Let me do this in a different color. That's the vector U. Okay, so let's find the vector V minus U. So would you rather do this by doing tip to tail, tail to tip thing? Or do you want to do it algebraically where we just mechanically figure out what the subtraction is? Do you care?
Algebraically.
Algebraically, because we'll get the exact answer. So let's do part A. Part A, let's do V, take away U. So we're just going to write the V vector down, 2, 3. We're going to subtract from it the vector -1, -4. And by what I said earlier, subtraction is very simple. You just have a new vector. You take the X component of the first one. You're going to subtract the X component of the second one. Then you take the Y component of the first one and subtract the Y component of the second one. So we're just doing this, take away that, this, oh, sorry. This, take away that. And we should get a vector, what is that, 3, 7? 3, 7. So let's see where that is. Let me graph that. Here's 3. 1, 2, 3, 4, 5, 6, 7. So right here, here's the result. Is that vector. How's that possible? Why is it way over here? I thought parallelogram, you're going tail to tip and stuff. Why is that way up here like this? What do you think
U is
subtracting does? Go ahead.
So U is negative.
Yeah, because you're subtracting, right? Because you're subtracting U, that's the same as adding. Another way you could look at this is that this is V plus -U. And so what you're really doing is you're taking V and you're adding to it the vector U, but pointed in the opposite direction. So what we're actually doing is taking that vector U, flipping it the other way, which will put it around here, and then attaching tail to tip, tip to tail, and that's why you wind up way up here. Okay, so you just have to be a little careful with that. I'm going to trust that you could do the next two. I'm going to just go to part D. So finally sketch the vector V, take away 2U. So we're just going to do this algebraically. V is the vector 2, 3. We're subtracting from that 2 times U. U is -1, -4. So what type of multiplication is this? This 2 here in front of this vector.
That's a scalar, right?
Scalar multiplication, yep. So you have two options here. You can just pass the 2 through and keep that a minus, or you can pass a -2 through and turn it into a plus. It's your choice. I'm going to leave the minus there and pass the 2 through first. Okay, so there's my scalar multiplication of this vector. And then I'm going to add these two vectors together, subtract these two by doing 2, take away -2, and then 3, take away -8. And so you should get a vector 4, 11. Any questions? Look, this is all very straightforward what we're doing, okay? And we're actually going to get into some much more like Cal 3 like stuff. We're just trying to get all these little things out of the way before we actually get there, all right? So be patient if you're bored. Okay, moving along. I'm not going to do the 3-dimensional one, but you know what? We should do a magnitude, don't you think? I think maybe we should do just a quick magnitude. Let's do the magnitude of this. If I asked for the magnitude of V minus 2U, so if I wanted to the magnitude of that, that means I'm talking about this vector right here that we just found, this one. So that means I want the magnitude of the vector 411. That's the way I'd write that, which should just be equal to the square root of, and I just take each of these components and square them. And then I'll add them together. So square root of, what is that, 16 plus 121? So square root of 137. And that's it. Now I could get that as a decimal, but I'm going to leave it like that. So that's how long that vector is. All right, moving along. All right, we have a new definition. Unit vectors. So any vector that has a length of 1 is called a unit vector. So any vector that's 1 unit long is referred to as a unit vector. So if I notice though that if I start with any vector, let's say I start with any vector like this blue one here, no matter where I position this vector, no matter how long I make it, do you agree that there is always a vector that points in the same direction that is 1 unit long? So you see the red one there? Do you see that that's 1 unit long? Now I could, I guess, add a little unit circle on here so you could see. There we go, that might help. So if I move this, no matter which direction I'm in, there's always a vector that's 1 unit long that points in the same direction. Now, what if I make this blue vector shorter? That's okay. You see, there's still a vector that points in that direction that's 1 unit long. It's longer than the blue one now, but it's still there. So no matter what, if someone hands you a vector, you should always be able to find that unit vector that points in the same direction. And to do it, we need some mechanical way of finding it. And we have a formula for it. So here's the formula for it. Given any vector u in either 2 or 3-dimensional space, we can always find the unit vector that points in the same direction as u by computing the following. So what we're going to be doing here is taking u and dividing it by its own length. Another way of writing that is, well, maybe I should point this out. Do you all agree that that's a number? The
Yes.
magnitude of u is how long it is, right? So I'm taking a vector and dividing it by its own length. Another way of writing that is to take 1 over the magnitude of u, which again is a number, and doing scalar multiplication. So I'm doing scalar multiplication of the vector u by 1 divided by its own length. So all you have to do is be able to find the length of the vector and then divide through. Let me show you with an example. Find the unit vector which points in the same direction as v. All right, so we have this vector v, and we need to find a vector that has a length of 1 that points in the same direction as that. So first thing I'm going to do is find its magnitude. So what is the magnitude of v? Well, it's just the square root of the sum of the squares of all of its components. So just using the formula I gave you a second ago. So this is 4 plus 9 plus 25. What do we have here? Is that 38? Yeah, 38. Square root of 38. Okay, any questions so far? That's how long that vector is. So to find a unit vector that points in the same direction, what I'm going to do is I'm going to take 1 over the magnitude of v, which is a number, and multiply it times v, the vector. And so this should give me 1 over the square root of 38 times the vector 2, 3, -5. Okay, so I'm scalar multiplication here. Now this just passes through to each one of those. So I have a vector, it's 2 over root 38, 3 over root 38, and -5 over root 38. This vector should point in the same direction as this one, but if you measure how long it is, it should be 1. Do you believe that that's true? You believe it? How could you check? How could you check to see if this is indeed a unit vector? How could you check?
You can find the magnitude.
Yeah, find the magnitude. Let's do that real quick. Let's find the magnitude of that. What is the magnitude of this vector? It better be what? Better be 1, right? Okay, so I'm going to take the square root of, and now I'm going to take each of these components and square them. So what happens if I square this? Square the top and bottom, right?
4/38.
4/38. Okay, next plus, now this one, square top and bottom,
9/38.
38. And then square the last one, -5 squared is 25/38. And if you add all those up together, you get 38/38, which is 1. So you get square root of 1, which is 1. Okay, so it works. Now we'll need that later. You'll need to be able to find unit vectors in the direction of a given vector. It'll be very important later for some partial derivatives that we'll be doing later. Okay, any questions? Haven't called on anyone yet today.
I have a question.
Yes.
So the formula for the unit vector, it's the actual vector over the magnitude of the vector equals 1 over the magnitude of the vector times the vector itself, right?
Yes.
So how do you know which side to use?
What do you mean which side to use?
It's like, for instance, that you found this is the unit vector by doing the 1 over the magnitude times the actual vector, that's the unit vector. How do you know if you have to use the other side of putting the vector over just the magnitude? Or is it like the same thing since
It's the same thing. It's the same thing. I think what you're saying is, okay, the original formula I gave you would be this. It would be the vector v over its own magnitude, right? Like that?
Yeah.
If you kept it like this, then you write the vector v, that's 2, 3, -5, and then divide it by its own length, which is √38. Then you would just put that, divide each of those by √38.
Oh, okay, okay.
And then that would give you the same thing.
Oh, okay, I understand.
Okay.
Thank you.
I only do it this way to stress to you that this is scalar multiplication. Just to show you that it really is just scalar multiplication.
Okay, I understand.
Okay. All right, now, in two-dimensional space, there are two very important vectors. All right, two really, really important vectors. They're called the standard basis vectors. And if you've taken any physics classes, you've heard of these. They refer to them as I hat and J hat. So here they are. I hat is the vector 1, 0, and J hat is the vector 0, 1. Those are the two what we call standard basis vectors in two-dimensional space. Now, what makes them so special and makes us use this little notation, it's actually I hat J. Sometimes they just write it like that, like I with the little hat like that. But it's important to understand these are vectors. I and J are vectors. And the reason they're so important is because every other vector in two-dimensional space can be written as what we call a linear combination of these two vectors. I will illustrate. If I take any vector, doesn't matter where it is, this black vector right here. Okay, let me just leave it right there. I hat, okay, I hat is the vector 1, 0. That's this vector right here, that green one right there. And then J hat is the vector 0, 1, which is this vector here. I can always create U by somehow scaling I. So in this case, I have to take I and multiply by 2.652, which creates this longer vector, and then take J and multiply it by 2.745 and make it longer. Now, if I attach I to J, either tip to tail, tail to tip, it doesn't matter. I'm going to create that vector U. Does that make sense? No matter which vector you ever draw me, I don't care where it is in two-dimensional space, I can always use I and J to create that vector. So we call those the standard normal basis. Actually, in this book, they call it the standard basis. any of you who have to take linear algebra, you might even be taking it at the same time as this class. This is called these two vectors. Ooh, these two vectors create what's called an orthonormal basis. And that means that not only are these vectors, they both have a length of 1. Do you all agree with that? They both have a length of 1. They're orthogonal to one another, which means they're perpendicular to one another. So they're orthogonal, which is where the word ortho comes from. Normal meaning that their length is 1, and basis meaning they can create every other vector in the space. So in linear algebra, we say that these two vectors span the space. I'm only saying this for people who might have to take linear algebra. Like I and J create an orthonormal basis. Now, do you think that we have the same thing in 3-dimensional space? Yeah,
Yes.
we do. The only difference is that when we're in 3-dimensional space, I hat now has to have 3 components. So instead of it being just 1, 0, it's now 1, 0, 0. J hat has to have 3 components. So now it's 0, 1, 0. And we have this additional K hat, which is 0, 0, 1. So every vector in 3-dimensional space can be written as a linear combination of those 3 vectors. And those also form an orthonormal basis for 3-dimensional space. So this is an example where what we can do is just see how it is that we can take this vector written in this notation. And by the way, this is the notation I will use for vectors throughout the rest of the semester. I stay away from I hat, J hat, K hat. I stay away from it. But you should be comfortable with the idea that you can go back and forth from one notation to the other. So let me show you how this works. If I take this vector 2, 3, -5, here's how I can write it using the standard basis vectors. So I'm in 3-dimensional space, so I need to use I hat, J hat, and K hat. So just tell me if you agree with this or not. First, I'm going to rewrite this like this. And you just say, yeah, that's, that makes sense, or like, no, what are you doing? So I'm asking you to not ask why I'm doing it, just ask me, answer whether or not you think this is true. Like that vector is these 3 added together, right? Because you just add each of the components. So 2 + 0 + 0 gives you the 2, 0 + 3 + 0 gives you the 3, 0 + 0 + -5 gives you that. Yeah? Okay, now what I'm going to do is I'm going to factor out of the first one, I'm going to factor the scalar 2 out. On the second one, I'm going to factor the scalar 3 out. And on the last one, I'm going to factor the scalar -5. So I'm going to actually write -5, 0, 0, 1. Okay, so I could do that, right? If I do that, it's the same thing. And now all you have to do is recognize that this is I hat. And this is J hat. And the last one is K hat. So when you see this here written like this, 2I hat + 3J hat - 5K hat, that is the same as this vector. Those are the same things, 2 different ways of writing the exact same vector. All right, the reason I don't use this is because to write this, we have addition and subtraction in between these. Here it's just 3 components and angle brackets. I personally like to work with this more than I like to work with this. Oh, sorry, can't undo that, I apologize. Well, maybe I can. Did anyone need that? There we go. Good. Okay, now I'm going to clear it. Yep, okay, that's the end. That's what I thought. So that's it. Introduction to vectors. Now we're going to move on to the next section. And remember, I said that when you are given a vector, you're told you can add 2 vectors, subtract 2 vectors. And now we know how to multiply a vector times a number. So we know how to do scalar multiplication. That means we're going to take a number times a vector v. We know how to do that, right? But what if I give you two vectors, u and v, and I ask you to multiply them together? How do you do that? Right? That seems like a natural question. We also know what it means when you take a number and multiply it times a vector. Visually, we understand that that just scales the vector, stretches it out, shrinks it, might flip it over. But when you take two vectors and multiply them, what do you get? Like, what does that look like visually? Right? Now, this is actually pretty profound because this somehow gets lost in things when people start talking about vectors. So I'm going to just ask one more time for you to think about this. When you're given two numbers back when you're a kid and you're asked to multiply them, what do you get?
You get a number.
You get a number, right? Here, when I take a vector and multiply it, a vector times a number, what did we get?
A vector.
A vector, right? Here, I'm going to take two vectors and multiply them. What do you think we're going to get?
A number.
We're actually going to get a number sometimes. Sometimes we get a vector. You know why? Because there's two types of multiplication. We don't have that in our number system, right? When I ask you to take 3 times 4, you don't ask me, well, what multiplication are you talking about, right? Like, it's just the multiplication that we all know. When it comes to multiplication of vectors, there's two types. There's what we call the dot product, and then the other one is called the cross product. All right, so this is new. Like, this is not stuff we've seen before. Nothing's ever behaved this way. Even when we were dealing with functions, when you multiply two functions, you get a function, right? You don't multiply two functions and then ask me, oh, well, what type of multiplication? And you know, it's very natural. This is the first time we've ever run into something like this, where we're taking two vectors. We're gonna have two different types of multiplication. One's called a dot product, the other one's called a cross product. And we're gonna find in a second, we're gonna talk about the dot product today, that when you do the dot product, your answer is a number. But when you do a cross product, your answer is a vector. And I think it would be very natural for everyone to say, well, what does this number mean, right? Like, if you had to take two vectors and multiply them, doing a dot product, and I get a numerical answer, like, what does that quantity represent, right? And then if I do a cross product and I take two vectors and do this cross product and get a vector as an answer, what does that represent? Can I visualize that vector, right? So I hope that I've made it clear that there are two types of multiplication when it comes to vectors, and we are going to focus our attention right now on the first one, which is the dot product. All right.
On the symbol for cross product is an X, right?
Yeah, it's an X. I just didn't want to give it away yet, because the dot is like multiplication, right? But then that X used to be multiplication when we were grade school, right? But now we use it again, but it's two different notations, mean two different things, dot and cross. All right, here we go. Let's bring up the notes for dot product. Okay, the dot product. Some of this is going to be repetitious. Okay, the dot, also known as the scalar or inner product, works this way. You're given two vectors in two-dimensional space. We define this new type of multiplication between them as follows. If you take u and dot it with v, all you're going to do, and this I think again is very natural, is you're going to take that component and multiply it times that component. Okay, seem natural? You're going to get a number there. Then you're going to add to it. Do not forget, you're going to add to that now these two numbers multiplied. And your answer is a number. So there's no vector here as an outcome. This should bother you. I mean, I don't know. Maybe it bothers me more than it bothers you. But this is like, to me, this is like you take two cats and you breed them and you get a dog. You know, so like, what the hell's happening here? It just doesn't seem right. But it's going to have meaning, okay? It's going to have meaning. There's nothing, I mean, yeah, I'm just going to shut up. Let's just keep going. Okay, so the dot product is the sum of the products of the components It is vital to notice that it yields a number, right? Not a new vector. Also notice that we use a bold dot when we do dot product. So usually this dot here, it's bold. So like if you're reading a textbook, it'll be like bolded dot, not to mistake it with like a non-bold dot, which usually means like multiplication by a number. Okay. Now, if we're in three-dimensional space, it works the same way. Okay, you're going to take the first components, multiply them together, then add to that the second components multiply together, and then the third components multiply together. You add those all up and you get a number. So we're going to do one quick example, and then we're going to talk about what the hell it means. Like, what does the dot product give you? What's the significance of the number? And it's going to be significant. It's going to be very significant. All right, so let's do this dot product. U dotted with V is going to be, notation-wise, the U vector is -3, 4, 7. We're going to dot that with 2, -3, 5. And that just means I'm going to take the -3 and multiply by 2, then add to that the 4 times, 4 times the -3, and then add to that the 7 times the 5, which gives me -6 minus 12 plus 35. So what does this give us? -18, 17?
That's what I got.
Yeah, 17. So I can see some of you, which I told you, I'm keeping track of who's got their camera on. And I can see that some of you are a little bit bored because you've done dot products, you know how to do them. So for those of you who are bored, can somebody tell me any consequence of that answer being 17? Can you tell me anything now that you know the dot product is 17? Can you tell me anything about those two vectors? Because it's one thing to know how to do it, but when you learned it, did you learn the most valuable part of this answer? There's something significant that we can say now. I mean, right now we can draw, if we visualize these two vectors, there's something I can say about them.
The area of the parallelogram that they make is going to be the number of the dot product.
You're in the right ballpark. It has more to do with the angle between these two vectors. Right now, because this answer is 17, I know that if I were to take both vectors and attach them tail to tail, that angle between them, I can say is something because of this answer.
You can say
Yeah.
it's acute.
It's acute. Good. Okay, that's what it's gonna. Now I haven't told the rest of the class this. It's just, I know some of you have done dot products, but I want to see if anyone understood like what the big significance of that number is, which is the fact that the answer is positive tells us that the angle between those two vectors is acute. That means smaller than 90 degrees. Okay. Now I'm going to reveal that to the whole class in a note, but that's just mechanically, that's the dot product. We get this number, it still has no meaning to us at this point. Good answer. All right, next note here. All right, some properties of the dot product before we get into its main, like why it's useful. If you ever take a vector and dot it with itself, okay, if I take a vector and dot it with itself, what would happen? So imagine you have a vector u, which is the vector u1, u2. If I dot that with itself, that would be this. You would take the u1s, oh, sorry, this is three-dimensional. Let me erase that. So if I dot them with itself, you're just going to take that, multiply times itself, times self, times self, and then add them up. Right? Why is that the magnitude squared? What is the magnitude of that vector? What would be the magnitude of the vector u? Wouldn't that just be square root of u1 squared plus u2 squared plus u3 squared? Isn't that what the magnitude of u is. And if I square that, the square root goes away. And so you have u1 squared plus u2 squared plus u3 squared, which is exactly what dotting the vector with itself is. So this is a property of the dot product. A vector dotted with itself is always equal to the square of the length of the vector. What is the next property saying? Dot product is commutative. U dot v is the same as v dot u. So it doesn't matter the order you do dot products. Property 3 has to do with the fact that if you want to take two vectors, u and v and w, and add them together and then dot them with a vector, you could have just distributed this dot product through the parentheses, dotted those, and then got the answers and added them up together. So this is like a distribution. Scalar multiplication works kind of the same way. It doesn't matter where you scale. You could scale u by c and then dot with v, or you could dot u and v together first, then scale, or you could even scale the v and then dot it with u, and it would all give you the same answer. So scalars can be moved anywhere you want whenever you're doing dot products. And then the last one is that if you take the 0 vector and dot it with any vector, you get 0. All right. Okay, so why don't I give you, I don't know, 4 minutes to work that? I'm going to give you 4 minutes, see if you can just work what this is. This is just a mechanical exercise to make sure you kind of understand how to add and scale and dot and all that. So I'll let you work that. 4 minutes, 2 o'clock. So in about 3 minutes, I'm going to call on 3 people. And hopefully one of the 3 will have the answer to this. And then we'll all either agree and cheer, or we'll like boo them out of the room. We'll see. Still going to give you another minute or 2, but I'm going to be calling on Damien, Margie, and Daisy. One of you 3 hopefully will have an answer for me. Okay, what do y'all got? Damien, Margie, or Daisy? Any volunteers?
Yeah, I'll take a crack at it. I got 30.
30? Okay.
Yeah.
I got
Any objection?
39.
39? Let's make this, anyone got anything else?
Just anyone or
Yeah, anyone now, anyone.
I got -90.
Negative 90,
I got -90 as well.
negative 90 as well.
Me as
I got
well.
30.
30. Oh, wow. Maybe we need to work through this then. I think we have enough variation that perhaps we need to work through this. Okay, let's work through it. All right, so you can do this different ways. I'm going to do this first. I'm going to go 3 times u. Okay, so I'm going to take 3 times the vector u. There's the vector u. Now I will be dotting that with the vector v, which is the vector 2, -3, added to w, which is the vector 4, 0. Okay, so that's just me kind of rewriting the whole problem. Now, this right here is scalar multiplication. The 3 just goes to each component. So this becomes the vector -9, 12. Are we all good with that? Okay, dot that with, now over here in the parentheses, I need to add those 2 vectors together. So you just add their components. 2 plus 4 is 6, so I have a new vector 6. And then -3 adds 0, I get -3. So that's these vectors added. Now I dot them, right? And to dot them, I'm going to take the first component and multiply times first component here. That's going to give me -54. And then I'm going to take this component 12 multiplied times -3. So I'm adding to this, whatever I get when I multiply those, it's -36. So -90. Okay, so if you got something different, just make sure you understand where you made that mistake. Are there any questions?
Yeah, I have a question.
Go ahead.
So since there's not a vector line above the W, is it not just the magnitude?
Oh, right here?
Yeah.
That's actually a mistake. That should be
Oh,
done.
okay.
Yeah, no, because you can't add a vector to a number. You can't,
Okay.
you can't take, yeah, that must have got deleted somehow. I don't think anyone has ever brought that to my attention until right now, so I appreciate that, Damien. No, this has to be, like, what I'm getting at is you can't do this. You can't take the vector v and add to it a number, let's say 10. You can't put those together,
Okay.
okay? You can multiply by 10, but you can't add 10. All right, so that's it. Let's continue. All right, so dot product theorem, very important theorem here. This is our first theorem, I think, of the class. If theta is the angle between 2 vectors, u and v, so we have a vector u, and we have a vector v, and we put them tail to tail, okay? So if we arrange, remember these vectors can be moved around, up, down, left, right, but if we attach them tail to tail, and we talk about the angle between them, then here, this is, the following is true. That u dotted with v must equal the magnitude of u, the length of u, times the length of v, times cosine of the angle between them. Now, this theorem, this formula comes from pre-cal. You can do this by setting up a law of cosines on a triangle to do this. And the book actually does go through the proof of this. I'm not going to go through the proof, but it can be proven with relative ease that this is true. Now, it's a major result though. It's a major result because if you have that equation, you could always solve it for theta, couldn't you? Like if I asked you to solve this for theta, let's see what we would do. This is multiplication. Couldn't I divide both sides by magnitude of u, magnitude of v? Couldn't I do that? Divide both sides by that?
Yeah.
And so I'd have this. I'd have u dotted with v over the magnitude of u times the magnitude of V equals cosine theta. And now to get theta by itself and no cosine, I would just take the inverse cosine on both sides, or arc cosine. So I take the inverse cosine on the left, and when I do inverse cosine on the right, it kills the cosine, and I now have a formula for theta. That's going to be the next note, but I'm just trying to get you to see, like, this is a major result because it allows us to actually find the angle between two vectors. All right, so what are some of the results of this theorem? Given two vectors, the angle between them must be between 0 and pi. So that's the first thing we have to get straight here. If you give me a vector and you give me some other vector, if we attach them tail to tail, the angle between them must be between 0 and pi. Do you agree that that has to be true? Because pi is 180 degrees, so that would be the worst case scenario. Like the worst case scenario would be I take this vector and the vector pointed in the opposite direction. Then the angle between them would be pi. If you go any bigger than pi, then the other angle on the other side is smaller than pi. Does that make sense? So that has to be true. Now think about the cosine function from pre-calculus restricted on the interval 0 to pi. So I'll draw it for you just in case you've forgotten what cosine looks like. That's what cosine looks like. Between 0 and pi, I'm just asking you to be looking right here. Right? So think about this. If I'm saying that the dot product is equal to the magnitude of u times the magnitude of v, sorry, that's, oops, I should go back. If the angle between them is 0, okay? So if the angle between the two vectors is 0, that means they're pointed in the same direction, doesn't it? Okay, then cosine of 0 is 1. You can tell from the picture. So this formula just becomes u dot v is equal to magnitude of u, magnitude of v, cosine of 0, which is 1. So it's just the magnitudes multiplied together. So if the two vectors are pointed in the same direction, then the dot product is just the magnitudes multiplied. Now, what if the angle between them is pi over 2, which means that the angle between them, they're hitting each other perpendicular. This is the big one. What is cosine of pi over 2? Cosine of pi over 2 is 0, isn't it? That's right here on our picture. Cosine of pi over 2 is 0 means that when you dot the two together, you're always going to get 0 as an answer. And that is probably the major result of dot products, that right there. What we're saying is that the dot product of two vectors, if the dot product of two vectors is 0, we can say that those two vectors are perpendicular to one another. Always. Another way of saying that is to say u and v are orthogonal. That's another word for perpendicular. You'll hear me use that word more than perpendicular. U and v are orthogonal if and only if the dot product is 0. If and only if. That means if they're perpendicular, the dot product is 0. If the dot product is 0, they're perpendicular. It goes both ways. So it's like the ultimate result. Now, if your angle is smaller than pi over 2 between 0 and pi over 2, then cosine is always a positive number between 0 and pi over 2. So you're going to wind up having the magnitudes multiplied by a positive number, which gives you a positive number. And if the angle is between pi over 2 and pi, then cosine is negative, so you're going to get a negative number. And this is what I asked earlier. If you're confused, don't worry about this. This is what I asked earlier because I was seeing if anyone knew this. I'm going to show you with the visualization here. Here are two vectors. Okay, here's this vector. Here's another vector. Right now I have the computer calculating their dot product for us. Okay, so this is the actual dot product right here. It's a little too big, that's why it doesn't look like. So, yeah, so here's the dot product. Right now the dot product is negative 5.8. watch what happens as I move this vector around, as it becomes closer to orthogonal, closer to perpendicular. Look at that number. It's getting closer and closer to what?
0.
Right? And then eventually when they are perpendicular, oh, I can't get it quite perpendicular, but when they are perpendicular, your dot product is 0. It's negative when the angle is obtuse, 0 when the angle is pi over 2, and it's positive when the angle is acute. All right. So what if I go to the other side? Remember I said, what happens if you go past pi? You go past pi, now we're talking about that angle. So it's still smaller than pi. What if they point in opposite directions? What's cosine of pi?
1.
Close.
-1.
-1. Which means that the dot product would be the lengths of the two vectors multiplied together and then make it negative. All right, this is just a quick example. If the magnitude of, if I tell you the magnitude of V is 7, and the magnitude of U is 3, and the angle between them is 31 degrees, then what's the dot product? So this is just make sure we know how to use the formula. So U dot V is equal to magnitude of U times magnitude of V cosine of the angle between them. So if I know that the magnitude of U is 3, and I'm told the magnitude of V is 7, and I'm told the angle between them is 31 degrees, then I just need my calculator to do this. 21 cosine of 31. And I would make sure I'm in degree mode on my calculator, right? Because it says 31 degrees. I type that in and get that. Let me just tell you what that is. That way you have it. 21 times cosine of 31. It's about 18.0005. So nothing crazy there. We're just using the formula. The next one, a little more interesting. The question is, are these orthogonal? So, Maribel? Are you there, Maribel?
Yeah.
Yes.
Yeah.
Yeah.
Yeah. Can you hear me?
What?
Can you hear me?
I can hear you.
Okay, cool.
You just sound like you're suffering or something.
Oh,
You all right?
No, I'm suffering.
Okay. So, Maribel, this question is asking whether or not these two vectors are orthogonal. So what do we know about two vectors being orthogonal? What must their dot product be?
A number?
Okay, what number? This is the main point that you have to take away from what we just did. Two vectors are perpendicular if and only if their dot product is, just take a guess.
I have
Is-
no idea.
No idea. Give me a number between 0 and any number.
1.
Okay, 1. What do y'all think?
0.
0. It has to be 0. So Maribel, you're never going to forget this again now. Two vectors can only be orthogonal if their dot product is 0. So if I want to know if these two are orthogonal, all I need to do is take the dot product, right? So let's just take the dot product of these. What's V dot U? Okay, let's check. That's going to be 2, 4. We're going to dot that with 6, -3. So I multiply the first two together, that gives me 12. And then I add to that the second two multiply together, that's -12. Hey, voila, look at that. Voila. 0. Are they orthogonal?
Yes.
Yes, they're orthogonal. Isn't that a very, very easy, fast way to see if two vectors are orthogonal? It's very quick. Okay, next topic or next problem. U is the vector 2, -2, 6. V is the vector A, 3A, -2A. Find A such that these two vectors are orthogonal. Somebody tell, well, let me ask Juan. Is Juan around?
Yes,
Okay, what do I need to do here, Juan?
not sure.
Not sure? Okay, so if I just gave you two vectors and asked you if they're orthogonal, you would be taking their dot product and setting it or and figuring out if it was 0, right?
Yes,
Okay, but here, one of the vectors I gave you has a variable in it, right?
yes,
But don't you still need that U dot V? Don't you still need that this, when you dot them, you get 0?
yes.
Right, for them to be orthogonal? So tell me, what would the dot product of these be? Can you tell me that part? If I were to dot these, let's just take it slowly. You would take 2 and multiply by A, right?
Yeah, 2A,
2A, okay, plus the next piece would be
-6A,
-6A. I'm going to just rewrite this, -6A. And the last piece would be
-12A,
-12A. And what do you need that to all be equal to?
0.
0. Okay, this is just a linear equation. That's all it is, right? Let's collect all these together. What would it have to be here? Or what would that be? -16A? Must be 0, right? But there's only one way that that's true. And what is it? If A is what?
If A is 0.
A is 0. So if A is 0, what does the vector V have to be? 0, 0, 0, right? So if I give you the vector U, and I tell you that the vector V has to be A times 3 times A times -2 times A, and they need to be orthogonal, the only way that's ever going to happen is if the vector you're using up here for V is the 0 vector. Remember, that's the 0 vector, right? That's the 0 vector. This is a somewhat boring problem, but this is a good example of how, let's see, where is it? Here we go. Your mini exam, your first mini exam, look at this question here. Find the value or values of B which make these vectors orthogonal. So basically what I'm asking is, what does B need to be in order that when you dot these two together, you get 0? So you got to dot these together and figure it out and enjoy that, okay? Because you're going to get a pretty weird equation, and I'm very curious to see how you solve it. I expect this problem to be done without a computer, okay? I think my instructions say that too. Now, when I say no calculator computer, you can use your calculator to do arithmetic, cosine, sine, you know, square roots, things like that. But you can't go to like some website and have it solve some crazy equation for you. All right. So I'm curious to see how many of you can get the equation that you get here and solve it by hand. I really want to see what you can do. So this is a good example of how I just gave a very basic kind of ridiculously easy problem here, but on the mini exam, it's going to be something significantly harder. But as long as you understand what you have to do, it's the same setup. U dot V has to be 0. Solve. Okay, moving on. So this is that other result that I told you. If you're trying to find the angle between two vectors, then all you have to do is do the inverse cosine of U dot V over the magnitude of U times magnitude of V. This formula gives us a way of finding the angle between two vectors. Very nice and useful. I'm going to skip to this one. If U is 2, -2, 6, and V is -4, 4, -12, determine if these two vectors are orthogonal, parallel, or neither. So let me ask something. And it's going to go to Donald. Donald there?
Yeah, I'm here.
Okay, there you are, Donald. So you've already responded today, but I'm going to ask you, if you were going to check to see if these were orthogonal, what would you check?
I'll check his dot product.
Okay, and check to see that it's 0, right?
Mhm.
Let's say you do that and it's not 0, right? Then they're not orthogonal, right? So then you have to see if they're parallel. How would you go about seeing if they're parallel?
I know it'll have to come out to 1.
What would have to come out to 1?
I would say maybe the dot product. That'll be the result of 1.
If they're parallel, well, okay, let me ask you this, Donald. What does it mean for two vectors to be parallel? They must be.
Sorry, I lost my thought. They have to be scalar multiples of each other.
There you go. Perfect. Okay, so let's go about this one thing at a time. Donald said he's going to check to see if they're orthogonal, going to do the dot product. I'm going to let you do that, Donald. I'm going to just let you guide me. So right now we're checking for orthogonality. We're going to dot these two together. So real quick, Donald, if I dot, I'm going to get what here?
-8.
-8 plus, right? And then
Plus -8.
-8. Okay, and then plus
That's 24.
negative, what is it?
Oh, my bad.
That's right.
72.
-72. Okay, I think it's obvious. Is it obvious, Donald? This is not 0?
Yeah.
Okay, so this isn't 0. Okay, everyone, good. You're off the hook, Donald. So Donald has helped us determine that they are not orthogonal. Okay, so let's see if they're parallel. So Jorge, is Jorge here?
Yes, sir.
Yes, sir. Okay, very good. So parallel, Donald said that to be parallel, they have to be scalar multiples of one another. Can you kind of help elaborate on how we might go about determining that? Or maybe think of it another way, like how can I move forward here with checking this?
I would check to see if some of the components have common multiples.
Yeah, exactly. Perfect. I don't think I could have said that any better. So if we look at if we look at these numbers, okay, look at the number 2. Is there a way that I can multiply that by something to get -4? So what would I have to scale 2 by to get -4?
-2.
-2. Okay. Is there something I could scale -2 by to get +4?
Also -2.
Also -2. What about 6 turning into -12?
Also -2.
-2. So it appears that if I take -2 and I scale the original vector by -2, I get the other vector v. Do y'all see that? If I take this vector, scale it by -2, I get the other vector, which means that these are scalar multiples of one another, which means they're parallel. It's not as easy to check for parallel as it is to check for orthogonal, in my opinion, because for orthogonal, you're just looking for a dot product to be 0. That's it. But for parallel, you have to see that it's a scalar multiple. And sometimes it's not as easy as, just -2. What if this number here, what if this number in the second vector, what if that number right there had been +12? And this wouldn't have worked, would it? Right? So then we would say they're not parallel, and then your answer would have been neither. Because you don't have to be orthogonal or parallel. It's not one or the other. There's a third option, that's neither. All right. Moving on. All right. I like this problem a lot. I'm going to put you in breakout rooms, and I'm going to see if you can talk through these. I'm not going to give you any more direction other than to tell you what you have learned today. You have enough to do this. All right. But you want to use what you've learned today. You don't want to be trying to use some obscure thing from pre-cal or something like that. You can do everything that's being asked here with what we've been presented with today. So I'm going to do breakout rooms probably for the next 10 minutes. Then I'll pull everyone back together and we'll see if we had a path, a way of getting this. Make sure you copy the problem down. I'll give you a moment to do that. I'll be making the breakout rooms. Let's see here. Go for about 4 people per room. There you go. Should be open. Lorraine, are you there? Lorraine? Okay, we just got waiting on a few more people to come in. All right, so I think only one group got this just right off the bat, and I didn't get a chance to go into the 5th room to talk with you all. So class is pretty much done at this point, but I'm just going to run through this very quickly. The idea, I give you 3 points. I give you 3 points, not 3 vectors. They create a triangle in 3-dimensional space. What you have to do is you have to check each of these angles. We'll call that theta, we'll call that alpha, we'll call that beta. You have to check these angles and see if any of them are 90 degrees. So the first thing I would want to do is let's check theta. I have to create the vector that goes from here to here, create the vector that goes from here to here. Those you have to do by using what we did last class. How do you create a vector from 2 points? Once you create those vectors, call them u and v. All you have to do is dot them and see if you get 0. If you get 0, you're done. You have a right triangle. If you don't get 0, you move on. Now you check alpha. So now you have to create 2 new vectors and do the same thing. If you get 0 as a dot product, you're done. If you don't, you move on to beta. So you have to create 2 new vectors and then dot those. Right? Yeah, that's it. So there's the main thing I wanted everyone to understand is the difference between me giving you points versus vectors. If I give you points, you have to create the vectors. Right? Question, Jorge?
Would you have to find 2 new vectors for?
Not necessarily. You could use the same vector because it doesn't matter their position, but you should practice creating the vectors just for practice, like creating the vectors from the points. Because they're parallel, you could actually use them. You like reuse the ones you had before. You would have to do something different for this one though. You couldn't use these 2. You could, well, I've drawn so much shit on the screen, it's confusing now, but like if you're trying to find alpha, you could reuse this vector, but you would still need that vector. You still need to go get that vector. Okay, so what I would advise as far as homework, make sure you've done everything in 10.1 and 10.2. This is 10.3. We're not done with 10.3. So for the 10.3 homework, I would say you're probably only good from, at least from what we've covered, you're only good up through, let me just look here real quick. 26. Yeah, you probably can only go up through like number 26. So 1 through 11, 13 through 26, you're not ready for 29, 35, or 36 yet. So we still have a little bit to finish up in dot product. In the next class, we start the cross product, which is that other multiplication. All right, everyone, we're already over on time. So thank you again for your participation. I'll hang out here for a minute if you have a question. If not, I will see you on Wednesday.
Yes, sir. Thank you.
See you on this, sir.
Thank you.
Have a nice day.
Thank you.
Bye.
Oh, so I had a question.